Hello seniors, today we're going to see electronic assignment number 12, which is Pascal's triangle and the binomial expansion. Remember we did a small introduction about this last week. I showed you a video about what the Pascal's triangle is about. And okay, so we're going to analyze in depth today what the Pascal's triangle and the binomial expansion are about, okay? This is usually a kind of difficult topic for students, so make sure you pay attention to this, because if you really understand the different concepts involved here, most of these exercises would be kind of easy, but you need to pay close attention to this. Okay, so Pascal triangle and the binomial expansion. The objectives for today: apply the binomial theorem and calculate binomial coefficient using Pascal's triangle and combinations. Okay, so let's start with a short investigation here. It says write the expanded form of a plus b squared and a plus b cubed. So how do we expand this first term, a plus b squared? Remember, this is the same as saying a plus b times a plus b, right? And then we could do FOIL method and we would get a squared plus ab plus ab plus b squared. So finally we would get a squared plus 2ab plus b squared. So this is the expanded form of this equation, this expression over here, okay? And then a plus b cubed. In that case, we would have to multiply this three times. And in order to not waste too much time, I'll just write the answer for the expansion, which is a cubed plus 3a squared b plus 3ab squared plus b cubed. So we're going to see in a while how you can remember this expansion easily using the Pascal's triangle. Okay, so what is the Pascal's triangle exactly? Remember I showed you this last week. The Pascal triangle is a triangle that is formed by adding the terms. Here it says any number in the Pascal's triangle is the sum of the two numbers immediately above it. Okay, so here we can distinguish rows in the Pascal triangle. I can add here what we call a row 0, and the expression would be just 1 here in order to add the top of the pyramid here. So we can analyze this. So row 0 is only 1, row 2 has row 1 has 1, 1. Then for row 2, you see that each term, we always have 1s in the lateral parts of the pyramid. And then the values in the middle are the addition. Here you see, for example, this 2 over here is the addition of 1 plus 1. Then this 3 over here is the addition of 1 plus 2. Then this 3 over here is again 1 plus 2, and so on. We can go to any number. For example, this 20 is the addition of 10 plus 10, and so on. So that's how we build the Pascal's triangle. And how is this Pascal's triangle useful? If you compare the investigation we just did with the Pascal's triangle, you would see that where do you see a plus b squared? It's exactly here, right? And take a look at the coefficients we have in the Pascal triangle. 1, 2, 1. And these same coefficients are present here, right? 1, 2, 1. Okay? If we take a look at the cubic binomial, we would see that this is a row in the Pascal triangle, and the coefficients are 1, 3, 3, 1, which are exactly the numbers we have here. 1, 3, 3, and 1. Okay, so that's the usefulness of the Pascal triangle. We can easily write, for example, the expansion of a plus b to the power of 7 just by looking at the coefficients over here. And pay attention that, well, this is something that we're going to see in a while. But for example, in a plus b cubed, you'll see that the first term, the a, always starts with the greatest exponent, in this case to the power of 3, right? And then the a goes decreasing its power by 1 until it reaches a to the power of 0, right? Which is the same as just not appearing. So, and the second value, which is b, you see that it first doesn't appear, so it's b to the power of 0, and then the powers go increasing, b to the power of 1, b to the power of 2, b to the power of 3, up to the maximum exponent, which is in this case the cubic power, okay? So that's how we use the Pascal's triangle. We're going to see all of these properties in a second. Here it says, can you predict what the numbers in the 8th row will be? So let's try doing that quickly here. The 8th row would be 8. The expression in this case would be a plus b to the power of 8. And the Pascal's triangle would be 1. 1 plus 7 is 8. 7 plus 21 is 28. 21 plus 35, that's 56. 35 plus 35 is 70. 35 plus 21 is 56. And this is 28, 8, and 1. Okay, so that's the 8th row of the Pascal triangle. And we can keep on doing this for as long as we want to. Then it says, here are the numbers in the 4th row of the triangle. 1, 4, 6, 4, 1, which is this row over here. 1, 4, 6, 4, 1. These numbers can also be found using combinations or the NCR function on the GDC. I'm going to show you this in a second, but in order to do the NCR function, you just need to press option, probability, and NCR. Okay, so for example, I'm going to show you this in the calculator. If we want to find the first thing, 4C0, 4C1, 4C2, and so on, what we're going to do is, if you go to the calculator, just a second, and then you go to menu 1, the main menu, and then you click on option, then you go to the little arrow, which is F6, and here you'll see prob, which is probability, F3, and here you have the NCR that we're looking for. So you click on F3, so you get the capital C over there. So in the left side, we're going to put the 4, and on the right side, we're going to put 0 in this case. This gives us 1. If we then change this to 1, we would get 4. If we change this to 2, we would get 6. And you see that we're getting the coefficients of the Pascal triangle, right? We get again 4, and if we put 4C4, we should get 1. Okay, so those are exactly the coefficients of the Pascal triangle. Okay, so that's a fast way, if you're using a calculator, to calculate the coefficients in the Pascal triangle. So it says, these are different ways of expressing the combination. We could write it as NCR, or we could write it also like this, NR in parentheses, like if it was a vector. And sometimes it is even written like this, NCR, vertically, okay? Then it says, NCR represents the number of ways n items can be taken R at a time. And here's an example. This is the real life application of this combination, or combinatorics is the name we give this. It says, for example, suppose a bag contains 5 balls labeled A, B, C, D, and E. If you reach in and take 2 balls from the bag, there are 5 balls in total, and we're taking 2 balls from the bag. So there are 10 different combinations of balls you could select. These combinations are A, B, A, C, all of this one, okay? So let's see if that's true. If I have 5 balls, let's call them A, B, C, D, E, okay? So I want to pick 2 of them each time. So how many groups of 2 can I make? The first option would be AB, right? So I'm going to write all of the possibilities. AB is one option. Another option would be AC. So AC is a second option. Another option would be, let me erase this, AD, right? AD. and also AE. Okay, so we're done with ball A. Now, with B, what combinations do I have? BA I already put here, so I cannot write this back. So I'm gonna put BC, this is the next option, BC. Then we have BD, and finally BE, right? Then we go to C. Once again, I cannot write CA nor CB because I already wrote those. So we have CD and CE. CD and CE. Finally, for ball D, I can join it with ball E. So my last option would be DE. So how many options do I have in total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is exactly the number we get by doing 5C2. We may do this in our calculators if you want, and you get 10. So this is a practical application of combinatorics, okay? And it's very useful in order to determine all the different possibilities when arranging different stuff, okay? Then we're given a formula here, which this is in the formula booklet, which let us calculate the combination of n items taken r at a time by using this formula. This is in the case in case we're not allowed to use calculator, or in case we don't know one of these two variables, okay? So the formula is basically n items taken r at a time equals n factorial over r factorial times n minus 1 factorial. Remember what factorial means? For example, if I want to find 4 factorial, do you remember what the factorial sign means? The factorial is basically multiplying all of the, starting from this number and then going back, okay? 4, 3, 2, and 1, okay? So this multiplication is equal to 4 factorial. This is 12 times 2, 24. So 4 factorial equals 24 in this case, okay? We're gonna see many examples of this for you to understand this. So here it says, the exclamation mark is the factorial sign. The expression n factorial is called n factorial. Okay, so let's see an example here. It says, find the value 7, 5 using the formula and check with your GDC. Okay, so first of all, we're gonna try finding this using the formula. So if we pay attention at the formula, it says that 7 items taken 5 at a time should equal to 7 factorial over 5 factorial times n minus r, that's 7 minus 5 factorial. That's the formula, okay? So how do we calculate this? 7 factorial is the same as saying 7 times, well, before doing that, it'll be easier if I first organize this. This is 7 factorial over 5 factorial times 2 factorial, right? 7 minus 5 is 2. So now, 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. Remember, we're not using calculator first. And then 5 factorial is 5 times 4 times 3 times 2 times 1. And finally, 2 factorial is 2 times 1. Okay, so you see here that many of the terms get simplified. All of this gets simplified with all of this, right? So we can simplify that. We can just cross this out. And finally, we would get 7 times 6 over 2 times 1. And this is easy to solve, right? 7 times 6, that's 42. 2 times 1, that's 2. So 7 items taken taken 5 at a time equals 24. So there are 24 different combinations in which we can take out of 7 balls, for example. If we take them 5 at a time, we could make 24 different combinations. Now, if we use our GDC to check, using GDC. Remember, I just showed you it's, I'm gonna copy the instructions. Option, probability, NCR. So let me show you here. So I'm gonna erase this, and then we go to option, probability, prob F3, and then NCR F3 again, and we put in 7, 5, and we should get 21. Oh, we may, yes, I made a little mistake there. I just realized that. I'm gonna take this to the class. 42 divided by 2 is actually 21, not 24. Sorry for that. Okay, so this is, let me put this here. So this is how you do it using the calculator. So finally, let me change this. 42 divided by 2 is 21. There you go. Okay. So we get the same result using the calculator. Now let's see some very important properties about the binomial expansion in the Pascals triangle. Pay attention to this. It says, we will look at what happens when we expand an expression like a plus b to the power of n, where n is a positive integer, and it could be any number, 1, 2, 3, 4, 100, whatever. Okay. In the investigation we did previously, you expanded this expression. So we saw how to expand this, right? A plus b to the power of 1, a plus b to the power of 2, and we saw that each of the coefficients in front corresponded to the coefficients in the Pascal's triangle, right? So here it says, if you look closely at each expansion, you will see some patterns. Number 1, the number of terms is 1 greater than the value of n. The number of terms is 1 greater than the value of n. What does that mean? If the power is to the power of 1, you see that I have 2 terms, right? 2 terms. If the power is to the power of 2, you see that I have 3 terms, right? 3 terms. And so on. If we go to the power of, if we go to the power of 5, we should have 6 terms, right? 1, 2, 3, 4, 5, 6, okay? So always we would have that there's 1 more term with respect to the exponent, okay? So that's one important property you should know. So this has 6 terms. So that's property number 1. Then number 2 says, the power of a begin with a to the power of n. That's the first term in the binomial term, okay? The powers of a begin with a to the power of n, and the powers of a decrease by 1 until you reach a to the power of 0. Remember that a to the power of 0 is 1 in the last term, okay? So that's what I already explained to you. For example, if we look at a plus b to the power of 4, a should begin at a to the power of 4, and then you'll see that the power of a goes decreasing by 1. a cubed, a squared, a to the power of 1, and then a to the power of 0, which is the same as 1, right? This is 1, so we just do not write that. So the power of the first term goes decreasing, and it always starts with the exponent of the expansion, okay? So that leads us to property number 3, which is exactly the opposite as number 2. It says the powers of b, remember b is the second term of the binomial. The powers of b begin with b to the power of 0, and the powers of b increase by 1 unit until you reach b to the power of n in the last term. So same thing, but in the opposite direction, right? b to the power of 4. We start at b0, and then this goes increasing. This is b to the power of 1, b to the power of 2, b to the power of 3, until b to the power of 4, which is the same as the exponent of the expansion, okay? So that's the third property. Okay. Then we have property number 4, which says the coefficients are all numbers from Pascal triangle. That's what I told you. All of the coefficients, this is 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and so on. All of these coefficients in front of the terms are coefficients from the Pascal's triangle. It says the coefficient of a plus b to the power of n are numbers from the nth row of the Pascal's triangle. You can find this using the triangle or the formula for combinations or the NCR function on the GDC. So there are different ways we can find these coefficients. The easiest way usually is just by building the triangle, unless we're asked to find, for example, a plus b to the power of 20. In that case, we would not build 20 rows in the triangle because it would take too much time. Although you can, but you will waste too much time. In that case, it may be easier to use the formula instead, okay? So, what that is telling us is if we have, for example, a plus b to a power of, let's say, 7, we need to build up to the 7th row, okay? As I showed you here at the beginning, right? A plus b to a power of 7, we go to the 7th row. Remember that row 0 is the one that has the 1 on top, right? Row 1 already has 1, 1, okay? So remember that and do not get confused. So the exponent tells us which row we should be looking at, okay? So remember that. Then, property number 5, it says, the exponents in each term add to the power of the binomial. The exponents in each term add to the power of the binomial. For example, in the expansion a plus b cubed, we get a cubed plus 3a squared b plus 3ab squared plus b to the power of 3, b cubed. So the exponents in each term add to 3. So you see that every time here we have a cubed, so this adds up to 3. Then this is a squared, this is b to the power of 1. 2 plus 1 is also 3. Then 1 plus 2 is also 3. And finally, 3 plus 0 is also 3. So every time, all of the sums of the powers should always give us the total power, which in this case is to the power of 3, right? But this could be to the power of 5. For example, if we look quickly at a plus b to the power of 5, you'll see that this is to the power of 5, 4 plus 1 is 5, 3 plus 2 is 5, 2 plus 3 is 5, and so on. The exponents should always add up to the exponent of the expansion. Okay, then it says, you can use these patterns to expand the expression a plus b to the power of 6. If we use the properties, we should know that, first of all, the expansion should have 7 terms, right? Number 2, we should know that the powers of a, the first term, will decrease and the powers of b will increase, okay? Property number 3, the coefficients in front will be the 6th row of the Pascal's triangle. Actually, yes, that's fine. The 6th row of the Pascal's triangle, which if we go look the Pascal triangle, the 6th row is this one over here. 1, 6, 15, 20, 15, 6, and 1. Okay, those are the coefficients which are written here. 1, 6, 15, 20, 15, 6, 1. So finally, if we use all of those properties, we would get that the expansion, a plus b to the power of 6, is the coefficient, which is 1, a to the power of 6. Remember, a begins with the maximum power, and b begins with the minimum power, right? B to the power of 0. Then second term would be 6, which is the coefficient in Pascal triangle, times a to the power of 5 times b to the power of 1 already, right? Then third term is 15. Then a to the power of 4, the exponent is always decreasing, and this one is always increasing. So b squared, then 20, a cubed, b cubed, then 15, a squared, b to the power of 4, 6, a b to the power of 5, and finally 1 times b to the power of 6, okay? So this is pretty mechanical. if you understand all of these properties, the problems that we're going to do next class are going to be much easier, okay? So please remember all of these properties in the Pascal's triangle. Let's read here. It says, for example, when n equals 4, the expansion has 5 terms. Okay, that's what we saw already. We saw this already. In a plus b to the power of 5, the coefficients 1, 5, 10, 5, 1 are the fifth row of the Pascal triangle. We already know that. Okay. Finally, we could generalize what we've seen in the Pascal triangle by stating the binomial theorem, which basically is what we just saw, but written in a mathematical way. It says the binomial theorem states that for any power of a binomial, where n belongs to the natural numbers, a plus b to the power of n equals the first coefficient in the Pascal triangle, which is n, the total exponent, and 0, because it always starts at 0 in order to get the first coefficient to be 1. Okay, then a has the maximum exponent, b has the lowest exponent. Then the second term would be the combination of n taken by 1 of a decreases in one exponent, so 1 minus n, or n minus 1 would be the new exponent, right? N minus 1, while b, instead of being 0, now increases to 1. And then we keep on doing this. The next coefficient would be n taken from 2, then a to the power of n minus 2 decreases in 1, and b increases, and so on, until we get to the last term, which is n taken n times, and the exponent of a is 0, and the exponent of b is the maximum possible, which in this case is n. Okay, so this is how we write the general formula for the binomial theorem, which is the Pascal's triangle. Okay, this is another way of writing this same thing. You see that we're adding all of the terms, adding. So we can generalize this using the sigma notation of this. Okay, and we're gonna see next class how we apply this in order to solve problems. Okay, so I hope that everything is clear. If not, you can always ask me in the Google Classroom, and I will try to answer you as soon as possible. See you.